Dear students, today's topic is probability, a very important topic in the branch of mathematics, especially applied mathematics. So, the word probability figures very often in our everyday speech and in a wide variety of context. For example, probably it will rain tomorrow, or we say probably he is an honest man. The probability that there will be a bumper crop in the next season is very small. What is the probability of a double six in a throw of a pair of dice, and so on. So there are so many words in our daily life that we use the word probability or chance. So before giving a proper meaning of the term probability, which can be used in science, we distinguish between two types of phenomena, namely phenomena whose future behaviors are predictable in a deterministic manner, and phenomena characterized by the fact that their future behavior not predictable in a deterministic fashion. So for an example of the first phenomena, we can say about the experiment of throwing a particle vertically upward with an initial velocity u, and there is an acceleration due to gravity acting vertically downwards g. So the greatest height attained by the particle is uniquely determined, and it is given by h is equal to u square by 2g. This is the greatest height attained by the particle. So if you repeat the identical conditions, that is with the same velocity u and with the same acceleration due to gravity, then you will you will calculate the same greatest height h. So I am using the term identical condition. Look at that, this is very very important in probability. Identical condition. So if I repeat the same identical condition, then the value of h will be same, but it is very difficult to maintain the same identical condition. So here we predict the weighted value of h with certainty in the initial velocity u and acceleration due to gravity g be known. We find that the experiments once performed cannot be performed again exactly under the same conditions, since in practice the value of the initial velocity u in any two trials cannot be made exactly equal. Look at that. But the variations in the values of u in different trials are very small, so that we can neglect such variations, and therefore in spite of such variation we state that the experiment is repeated under identical conditions. So identical conditions mean not exactly identical, but as identical as possible. Thus, in practice, the truth of the statement greatest height is same in every performance of the experiment under identical conditions can be verified only in the above approximate sense, and in this sense we can state identical values of u under identical given conditions yield identical values of greatest height. This is true for every such experiment. Okay, so if you do any experiment, then you will get this type of. So in this phenomena, the future behaviors are predictable in a deterministic manner. Now come to the next phenomena, that is future behavior are not predictable in a deterministic fashion. So for example, suppose we are tossing a coin. So if we repeat the experiment under identical conditions, it will be observed that the possible results will be either a head or tail. Here also we are maintaining the identical condition, and the exact prediction of the result in any particular trial is always impossible. So you cannot predict. So similar remarks can be made for this type, like throwing a die. In case of throwing a die, there are 1 2 3 4 5 6, so you cannot predict 1 2 3 4 5 6. So in case of throwing a die, your experiment is throwing a die. So what are the possibilities? The possibilities are 1 2 3 4 5 and 6, but in every trial if you maintaining the identical conditions, you cannot predict the exact. You can guess, but you cannot predict. So similarly, we can there is a experiment of drawing cards from a pack of cards, predicting a sex of a newborn baby, telling the number of particles emitted from a radioactive source in a given time interval, etc. So there is a randomness in the experiment. So now we'll define the random experiment in this case. So this is the very important definition in probability: the experiment or observation for which we know priori the set of all different possible results or outcomes, and which are such that it is impossible to predict which one of this set will occur at any particular performance of the experiment, are called random experiment. So if you know the results but which one of them will occur cannot be predicted, those experiments are called random experiment. Let us define the random experiment in a very compact form. So E will be random experiment if all possible outcomes of E are known in advance. You know all possible outcomes. It is impossible to predict which outcome will occur at any particular performance of E. Number 2, and number 3, E can be repeated at least conceptually under identical conditions for infinite number of times. So this is the very compact definition of E. So suppose tossing a coin, throwing a die. For tossing a coin, the outcomes are head and tail. You cannot predict which one of them will occur. For throwing a die, you have 1, 2, 3, 4, 5, 6, and you have a pack of cards. From pack of cards you are picking up a card. So this is also a random experiment. There is a, in a bag there is a different colors of ball. Without seeing the color you are drawing a ball. This is also a random experiment. So this is how there are so many experiments if we have that have randomness in their nature. So these are all random experiments. Now let us define sample space. The set of all possible outcomes of a given random experiment is called the sample space associated with that experiment. So it is just the all possible, if you take the all possible outcomes, then that gives you the sample space. Suppose in tossing a coin, head and tail, this is the sample space. In throwing a die, 1, 2, 3, 4, 5, 6, this is a sample space. So each possible outcome or element in a sample space is called the sample point or an elementary event. So now there is an important concept that can sample space be infinite? The answer will be yes. Now look at that. Sample space can be divided into 3 categories. One, sample space can be finite, sample space can be countably infinite, and sample space can be uncountably infinite. So for finite, you toss a die and observe the number that shows on top. So 1, 2, 3, 4, 5, 6. This gives you the sample space. So your sample space is this 1, 2, etc. up to 6. So this is your sample space. So this gives you a finite sample space. So you are tossing a die and the number shows on top, that gives you the sample space. In this case you are getting finite. Countably infinite, this is very, very important. Items are manufactured until 10 non-defective items are produced. So your sample space will be 10, 11, 12, etc. So this gives you a countably infinite, because until 10 non-defective items are produced. So your counting starts from 10. So there is a natural association with this space. So this is actually countably infinite. So any set that has a association with the natural number is bijective mapping, and that will be countably infinite. So toss a coin until a head appears. So this gives you a head, tail, head, so on. So this is actually countably infinite example. Also we have non-countably infinite. Suppose the life length of a bulb. So this gives you this is an interval actually. So a light bulb is manufactured and it is then tested for its life length by inserting into a socket, and the time elapsed in it burns out is recorded. So this gives you the life length actually. So this gives you t greater than 0, greater equal to 0. It may be life length may be 0 otherwise it will be any interval. So this gives you a non-countable infinite. Any interval is non-countable infinite. The tensile strength of a steel beam is measured. In this case also T greater or equal to 0 if the T be the tensile strength. So there this is also an example of an infinite, countably infinite sample space. Next we define event space. So many there is a concept that sample space and event space are different. Let us have the definition and also some examples to illustrate this. Let a random experiment have a sample space S. So your experiment is E and your sample space is S. Then by the event space of the random experiment we mean a collection A for subsets of S, collection of subsets of S satisfying the following conditions. This F symbol somewhere it can be denoted by delta. So following conditions are: S belongs to F, that is the sample space belongs to the collection. If A belongs to the F, AC the complementary subset is belongs to F, and if A1 A2 etc. belongs to F, A1 union A2 union etc. belongs to F. So this gives you the three conditions, and F is nothing but your sigma algebra or sigma field. So what is your event space? Is a collection of subsets of S, and F is the sigma field. So the elements of F are called events. The elements of F are called events. Now let us have an example. If S is equal to, suppose your sample space is 0 1, then F1 is phi 0 1 is one possible event space. F2 phi 0 1 0 1, that is a power set of S, is another example of sample event space. But F3, look at that F3, individually 0 and 1 subset is not, since violating the third condition, because their union is not belongs to F. So this gives you the idea of the event space. Is a very important concept. Sample space and event space are different, they are not equal. For finite sample space S, the most common choice for event space is the power set, as we see from F2. Power set is the collection of all subsets of S. So this gives you the event space. Let us have another example of events and samples space. In a random experiment toss of 3 coins, the sample space S is given by H, 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 T, etc. So these are suppose points, omega 1, omega 2. These we denote by sample points, omega 1, omega 2, etc. omega 8 at the sample points. So there are 8 samples point, and now 8 possibilities. So there are 8 sample points. Let us consider the following events associated with the sample space S. We are defining some events. Suppose E1 is 3 heads, E2 is 3 tails, E3 is exactly 1 head, E4 is exactly 2 heads, E5 is at least 1 head, and E6 is at least 2 heads. So what is your E1? E1 contains only one sample point, omega 1. E2 contains omega 8 because E2 is 3 tails. Similarly E3, you can say these are the sample points, and look at that E4, E5. What is your E5? E5 was at least 1 head, that means it contains 7 sample points except 3 tails, omega 8, and E6 is E1 union E4. So this is how you can define the events on the sample space. Next we define some important definitions related to probability. First we define simple or elementary event. Events which cannot be further decomposed are called simple events. Suppose head tail in connection with tossing a coin. So these are simple events, head and tail. Again 1, 2, 3, 4, 5, 6. These are all simple events in connection with throwing a die. If there is a simple event, there will be compound event. Compound event which can be further decomposed into simple events. Suppose if I say event phase, so this is event phase is an example of a compound event, because event phase can be decomposed into 2, 4, 6. 2, 4, 6 are the simple events, and odd phase can be decomposed into 1, 3, 5, also an compound event. So compound events can be decomposed into simple events. Certain event, an event which is sure to occur at every performance of the experiment is called certain event. That means every time you are doing the experiment, you are getting that event. That is called a certain event. So certain event is H. Suppose I am giving one example, H or T, that is head or tail in connection with tossing a coin. This gives you a certain event because every time you are doing the experiment, you are getting head or tail. 1 or 2 or 3 or 5 or 6. So this gives you 6. So this gives you another example of a certain event, because every time if you are doing the experiment, 1 or 2 or 3 or 5 or 6 will happen. Impossible event, which is not possible in experiment. So example, suppose you are throwing a die and you are getting 7, that is not possible. So that is an impossible event. Equally likely events. In any random experiment, a set of events is said to be equally likely if there is no reason to believe that any one of them is more likely to happen than the other. That means if you are doing the experiment, you are not favoring any event. Head or tail, you are not favoring head or you are not favoring tail. So head and tail are equally likely events. 1, 2, 3, 4, 5, 6 in connection with throwing a die, you are not favoring any event on the dice. 1, 2, 3, 4, 5, 6 all have the equal possibilities. So these are all equally likely events. Mutually exclusive events. What is mutually exclusive sets? Let us draw mutually exclusive or disjoint. So these two sets are equal, mutually exclusive, A and B. A and B are mutually exclusive. Their intersection is phi. Disjoint. Similarly, we can say mutually exclusive events. That is, events are said to be mutually exclusive if they can never happen simultaneously. Head and tail are mutually exclusive. 1, 2, 3, 4, 5, 6 all are mutually exclusive, because if head happens, tail cannot be. So if one of them happen, other cannot be. So never happen simultaneously. So these are all mutually exclusive events. Then even phase, odd phase is also mutually exclusive. What about non-mutually exclusive? Suppose I am giving you example even phase. So what is your even phase? 2, 4, 6. 2, 4, 6 is your even phase. And what is your multiple of 3? Suppose I am saying multiple of 3. So multiple of 3 is 3 and 6. So 6 is a common element in both the sets. So this is non-mutually exclusive. So I am defining a term again, non-mutually exclusive. Non-mutually exclusive. Next, we define exhaustive set of events. A collection of events is said to be exhaustive in every performance of the experiment, random experiment. At least one event belonging to the collection happens. That is, every time you are getting at least one event belonging to the collection. In set theory, the collection of events is given by A alpha. Alpha is the index set, alpha belongs to I. And if exhaustive, if and only if summation A alpha equal to S. That is, it gives you summation A alpha gives you the sample space S. Let us have an experiment. Example for that. Experiment is throwing a die, and collection of events, suppose A1, A2, A3 is exhaustive. How? A1 is 1, 3, 5, A2 is 2, and A3 is 4 and 6. So if you take the union of these three, you will get the sample space. So this is exhaustive set of events. That means every time you are doing the experiment, at least one of event belonging to the collection happens. So this gives you the idea of the exhaustive set of events. Let's comes to the last section of our discussion today. So various methods of combining events, obtaining new sets of events. So if A and B are events, their union is also an event which occurs if and only if A or B occur. Again, their intersection is also an event which occurs if and only if A and B both occur. Complementary event A bar is also occur if and only if A does not occur. And if there is a finite collection of events A1, A2, AN, then their union is also occurs if and only if at least one of the events AI occur. And their finite intersection is also occur if and only if all the events AI occur. Similarly, we can define for countably infinite collection, union is also happen if and only if at least one will happen, and also for infinite collection this will happen. So this is how today's discussion is on the basic probability, that is the basic concept of random experiment, event space, very important concept, sample space, and few definitions related to probability, basic probability. I hope this video will be helpful to you. So please subscribe my channel, and for please look on the next videos. So thank you all of you. Have a good day.